So welcome back. We're going to have our next speaker, Patrick Morris from Barcelona, telling us something about Hamilton cycles in Dirac hypergraphs. It's all yours.
Thank you. Thank you very much. And yeah, thank you for the invitation as well. So yeah, everything I talk about today is joint work with Amarja, Kathapurkar, most recently in Birmingham, and Guillem, who's in Barcelona also. And it came out of a trip of Amarja to Barcelona. So this is also an advertisement for people to come and join us in Barcelona to do some research. So yeah, so I'm going to start basic with something you probably all know, which is Dirac's theorem. It's a classic extremal theorem that tells you that if your minimum degree of a graph is large enough, then you have a Hamilton cycle, and this is the tight bound is n/2. So just in case, this is a graph, this is a Hamilton cycle. More usually, we draw it something like this. And we're going to be talking about hypergraphs. And when you try and generalize Dirac's theorem to hypergraphs, you have various options. So firstly, you have to decide what you mean by degree. And you have sort of, yeah, k-1 options for this, depending on some parameter j. So that's the definition. Here's a picture. So in this case, in the picture, we're looking at three uniform hypergraphs. And this would be the 2-degree. So you look at pairs of vertices and you count how many edges are in them, and then you take the minimum of all pairs of vertices. And in general, this is what you do. You look at sets of j vertices, count how many edges, take the minimum of all. And yeah, if j is k-1, we often refer to this as co-degree. If j is 1, then people refer to this as vertex degree. So you have options for your what degree you're interested in, what type of degree, but you also have options for what type of Hamilton cycle. So here's a picture again. On the left is kind of the loosest possible. It's what we call a loose Hamilton cycle, where always we take some cyclic order of vertices and some cyclic order of edges, and on the left they're intersecting in just one vertex, consecutive edges, and on the other sort of extreme you have tight Hamilton cycles which intersect in k-1 vertices, so consecutive edges intersecting k-1 vertices. And again, you have a sort of full range between 1 and k-1. You have some parameter L, which is controlling how connected consecutive edges are in your hypergraph Hamilton cycle. So this is what we call a hypergraph L cycle. And yeah, these two cases, the two extremes, are kind of the most where the most research has been done. Good. So now we can think about Dirac's theorem in hypergraphs. And Dirac's theorem that I showed you at the start happened in the 50s. It took a long time for any tight result to be proven in hypergraphs, so it's somehow much harder. There were two in 2006. I don't know exactly which one came first, but both looked at free uniform hypergraphs. Coulson showed loose Hamilton cycles, so they got this degree bound, and Rödl-Ryczynski-Semeredy did tight Hamilton cycles in the free uniform case. And both of these results are tight, so these are sort of the best possible up to the little o of 1 degree bounds. Okay. What about in general? So you can define this parameter. There's a lot of words here, but it's just the constant that you're interested in. So in the previous case, it would be 1/4 in this loose Hamilton cycle in free graphs, and 1/2 in this tight Hamilton cycle case. And you're interested in, this is sort of the optimum degree threshold, and you have all your parameters here. So the k is controlling the uniformity of the graph, the j is the degree that you're looking at, the j degree, and the L is the looseness of your Hamilton cycle. Okay, so L = 1 is loose, L = k-1 is tight. And today we're going to be particularly interested in loose Hamilton cycles. So let me tell you what's known. So this was the result on the previous slide of Coulson. After a bit of time, this was generalized to all k and co-degree. So j = k-1. by two separate sets of authors in 2010. And the next breakthrough was in 2013, which could do vertex degree for free uniform. And again, this was generalized, but it turns out that it's not really the vertex degree here that's generalizable. It's more that it's k minus 2. So in general, they can do all k and k minus 2. Okay, and this is actually all that's known for loose Hamilton cycles. And there's not much more. I won't go through the whole, the other types of Hamilton cycle, but there's not much else known in the other cases. So for loose Hamilton cycles, we just know the k minus 1 degree and the k minus 2 degree in general. Good. So now I want to talk about something a bit different, which is instead of sort of generalizing Dirac's theorem to hypergraphs, another line of research, which is to strengthen Dirac's theorem. So once you're above n over 2, Dirac tells you that you have a Hamilton cycle, but maybe you have much more than this. And this has been shown in many notions of being robust. So this is called being robust with respect to having a Hamilton cycle. It's known, for example, that you actually have many Hamilton cycles. There's a type bound known on the number, that's Cook-Lacan. It's known that you have many edge disjoint Hamilton cycles, so you can sort of almost decompose G into completely into edge disjoint Hamilton cycles. A lot of work recently, although this result goes back for Hamilton cycles a bit, is that if you take some graph above the extremal threshold and look at a random sparsification, so you keep every edge with some probability independently, then the resulting graph you end up with still has a Hamilton cycle, and this works right down to probabilities which are the sort of threshold in GMP. And the one that we're going to focus on today is that if you take some coloring, which is nice in some way, it's bounded, I'll explain what that means, then you find a rainbow Hamilton cycle in this graph. Okay? And this notion might seem a little bit out of nowhere for robustness, so I'm going to take a little detour to motivate why people are looking at things like this and why we're looking at this. So the detour goes back to Euler, who looked at Latin squares, and let me remind you what a Latin square is. It's just an n by n array with n symbols, each appearing in each column and each row exactly once. And so there's an example. And a transversal Latin square is a collection of entries with distinct rows, distinct columns, and distinct symbols. So in my example, these circled entries form a transversal. Okay, the rise of Brodel-Stein conjecture is a very famous conjecture from the 60s that posited that every Latin square has a large transversal. So n would be maximum, and there's examples which you can't quite get n, but you should be able to get n minus 1. So a really, really large transversal. And this is now, yes, so I wanted to tell you what this has to do with rainbow subgraphs. So many of you would have seen this before, but I'll go through it for those that haven't. So this conjecture is equivalent to saying that if you take a complete bipartite graph, you properly color it, and you use n colors, then you can get a rainbow matching of size n minus 1. So why are these things equivalent? Well, there's a bijection between Latin squares and properly colored complete bipartite graphs with n colors. And in this bijection, the transversals correspond to rainbow matchings. So let's see it. So in one direction. So here's a Latin square. You take the rows as one of the parts of the bipartite graph, the columns as the other part. You color the entries. And now an edge in this complete bipartite is colored by the corresponding entry. So if you look in row 1 and column C, you see blue, and so this edge would be colored blue. You do this for all edges, you get a proper coloring of KNN. Proper precisely because every symbol is appearing in exactly one row and one column. And if you think about it, a transversal corresponds exactly to a rainbow matching. So a matching in which every edge gets a different color. Okay. Um, and right, so this is a very nice equivalent formulation and somehow sort of easier to think about for graph theorists. And there's a conjecture again in this equivalent formulation, and it's now actually a theorem due to a recent breakthrough of Richard Montgomery, who solved this and very much thinking in the world of rainbow subgraphs. And there's a slight difference between this conjecture and what Montgomery actually proved. And this goes back quite a long way. So let me point this out. So in the conjecture, when you think about Latin squares, you're looking at proper coloring with exactly n colors. But actually what Montgomery proved and what researchers already in the 60s sort of believed was that this is not necessary. And in fact, just any properly colored complete bipartite graph should have a large rainbow matching. Okay, so this structure, this very strict structure coming from designs from Latin squares is not actually necessary. It's more about the properties of the coloring in the graph world. And let me rephrase that. So a proper coloring is just a locally one-bounded coloring, meaning at every vertex, you see at most one edge of each color. And if you think about it like this, then you can ask about other types of boundedness, in particular, global boundedness. So this was a famous result of Ehrlich and Spencer that showed that if you take a global bound now, so global meaning you just count the number of occurrences of each color globally, and some global bound is enough. So n over 16 is enough to guarantee now a full rainbow matching, so a rainbow perfect matching, the best you can hope for. Okay, and right, so let me point out that some order n bound. So if you're looking at global bounds, then you need order n, otherwise there may just not even be enough colors. There has been a bit of work to try and get the best constant here. So this is not the best constant known, it's been improved. But we're far off. So we know it can't quite be n, due to, so n would be the obvious, the necessary bound, but this is not sufficient. So this was shown by Prokofsky and Sudakov in there, showing that Stein's conjecture was not true. And from below, it's a bit better than 1 over 16, but not, I think it's still less than a quarter. So there's quite a gap there. It seems like a very hard problem to get these precise constants. Right, so that once we have this theorem, then we can ask sort of about general phenomena that mimic this. So we can play with what host graph we're looking at. We can play with what subgraph we're looking for. And in particular, there's a result of Albert, Fries, and Reed that did this for Hamilton cycles in complete graphs. Okay. And I don't say what the mu is here. It's not something crazy. It's, I don't know, 1 over 64 or something. Okay, so finally, let's get back to the robustness. And this is a result of Coulson and Perarnau from 2020, which shows that you can do this in non-complete graphs. You can do this as soon as you're above the extremal threshold. So there's two ways of doing this. You're kind of strengthening Dirac's theorem. Once you're above the extremal threshold, then in fact you're robust for a Hamilton cycle. You can find a rainbow Hamilton cycle in any bounded coloring. And it's also strengthening this Albert, Fries, Reed, which is the case for G being the complete graph. Okay, and so let me tell you our result. So what we do is generalize their result, so the Coulson Perarnau, to loose cycles in hypergraphs. So this degree condition is optimal. So this is the definition of this delta JK1 is the extremal threshold. And now the boundedness, the sort of right way to scale it is that you're sort of little low of n to the k minus 1 bounded. Again, some order n to the k minus 1 is necessary. Otherwise, there may not be enough colors. And then we can force this loose Hamilton cycle. And let me point out that we can show this even when we don't know the degree threshold for the minimum degree threshold for loose Hamilton cycle. So remember, it's only known for k and k minus 1, but our result proves this in for all possible degree conditions j. So yes, it's tight up to this point, this value of mu. It was known already for complete hypergraphs. This was a result of Dudek, Fries, and Ryczinski. And I won't say much about the proof, but it involves the local lemma, a lopsided local lemma. All these kind of proofs do. So that started with Erdős and Spencer, and kind of Coulson Perarnau noticed that you could do this in a non-complete setting. So originally, the sort of Erdős Spencer was kind of careful counting to show negative dependency when taking a random perfect matching. And to do this in a non-complete setting, you have to sort of use switching. So it's some double counting argument, and you want to kind of take a random copy, and your bad events are something like two edges of the same color. And you want to count the ways of locally changing this Hamilton cycle to get a new Hamilton cycle that doesn't have this bad event. So this is the kind of local switching idea. And we need to use absorption techniques because when you take a Hamilton cycle and you locally disrupt it to get rid of some bad events, you need to put it back together again. And so this, we need to use some absorption techniques. And let me point out a recent result of these authors, which allowed us to do this absorption in the setting of not knowing the minimum degree threshold. So they actually were looking at resilience in random graphs for random hypergraphs for loose Hamilton cycles, and they showed how to build absorption techniques, so to build absorbing structures, even when we don't know the minimum degree threshold. So this was very useful for us. Let me mention that this falls in a larger class of results. So there's a meta-conjecture of these authors that says that this should basically always happen. So if you're above an extremal threshold for some spanning structure, you take some bounded coloring suitably. This is sort of deliberately vague, whatever you need to be suitably, then you should find your rainbow copies of that spanning structure. And it's known for many cases. So Hamilton cycles and perfect matchings in bipartite graphs was done by Coulson Perarnau. Hamilton cycles in graphs, this is the result I previously mentioned. Factors in general hypergraphs, so disjoint copies of some F covering the whole vertex set, was done by these authors. And in graphs, there's even a blow-up lemma. So sort of everything you can do with a blow-up lemma, you can do in this rainbow setting. So bandwidth theorem, etc. So given these sort of list of results, somehow the Hamilton cycles in hypergraphs seems like the most the biggest thing missing. So we kind of understand graphs pretty well, but we didn't know how the Hamilton cycles was missing. So this was what motivated us to have a look at this. And I've got a little bit of time left, so I want to talk briefly about what is meant by suitable bounds in this meta-conjecture. So there's our result again. And as I said, if you're looking at k-graphs, sort of a global bound of this order is necessary. Otherwise, you just really might not have enough colors to get your rainbow thing. And getting the precise constant seems very hard, even in the complete case. So we're more interested in the type of bounds that are necessary. And sometimes this is not enough. So this is just looking at a global bound is not what a suitable bound should be, and you need a local bound. So this was observed first by Coulson Perarnau, Keevash, and Yepremyan. So they showed that for example, for a clique factor in a hypergraph, you might need some local bound also. And the construction there is sort of you order your vertex set, and even in the complete k-partite graph, complete k-uniform graph, you order your vertex set and you color every edge by its sort of first two vertices, say, that come in this order. And you can see that every clique there will not be rainbow if your clique is large enough. So maybe you need some local bound as well to force this rainbow thing. And actually their result for factors imposed this local bound for all F factors. So another thing we looked at was tight Hamilton cycles, and we have a construction that shows that there you also need a local bound. So a global bound will not be enough. So here's the precise result. It's for co-degree in free graphs, and above the extremal threshold is half, if you remember from Rodo-Rudzinski-Semmeredy. So these are hypergraphs which do have tight Hamilton cycles, but there's globally bounded colorings that do not give rainbow Hamilton cycles, tight Hamilton cycles. So yeah, my last 3 minutes, I want to show you this construction briefly. I think it's quite nice. So you take your vertex set in 3 parts of size n over 3, and you color the now 2 uniform edges within each part. Okay, and each one gets its own color. So so you have a rainbow coloring of k n over 3 in each of these parts. Now your hyperedges are all 3 uniform edges which intersect one part in 2 vertices. And the color of a hyperedge is precisely the color of that pair of vertices of that 2 uniform edge that they intersect in. Okay, so you can check that this thing has minimum degree 2/3. 2/3 n, minimum co-degree. And let me show you that it doesn't have a tight Hamilton cycle. So imagine that there was some embedding of a tight Hamilton cycle into this free uniform graph. Let's think about where these vertices can go. So without loss of generality, you have something like this, 2 consecutive vertices in different parts. Let's look at the next vertices. So if U3 was here, this is not possible because this edge just isn't in the hypergraph. If U3 is in this same part as U2, then it gets the color of U2, U3. And where do you go next? You can't go here because this edge isn't in the hypergraph. You can't go here either because this would be two edges of the same color. So in fact, you have to have U3 on the other side. So with U1, and this would be okay. But if you kind of use the same logic, then U4 has to hop across to the other side, and you can continue. But at some point, you're going to have to leave to U3, so you're, to the part at the bottom, and this will give you your 2 edges of the same color. Okay. So sorry, that was quite fast. Let me leave you with the conjecture for tight Hamilton cycles. So this is a result that shows that some local boundedness is necessary, but we don't know the positive result. So we want to know that if you're above an extremal threshold, then if you take both a global and local bound, then you get your rainbow tight Hamilton cycle. And it might be the case also that the local bound can be dropped when you're really dense. So the local bound being necessary might depend on the minimum degree. In particular, we don't have constructions, for example, in the case that I showed before, for minimum degree above 2/3. So in fact, it could be that once you're, and this would be quite interesting to kind of determine when this local bound becomes necessary. And I think that's where I'll leave it. So thank you for your attention.